Floating tongues of ice known as ice shelves function like gatekeepers, holding back massive land-based glaciers that stand to boost global sea levels as they melt. But ice shelves are prone to cracking and breaking, which was spectacularly demonstrated in 2002 when Antarctica's Larsen B ice shelf, larger than the state of Rhode Island, suddenly collapsed. Scientists have investigated a couple of possible culprits for shelf destabilization: warmer ocean waters that eat away at them from below, light-absorbing debris such as rocks and soil on the shelf's surfaces that can kickstart melting, and transient lakes of meltwater that absorb more sunlight than ice does and also exert stress on their surfaces. Computer models and laboratory simulations have shown stress from up to a couple million tons of meltwater can cause ice shelves to bend and potentially fracture, but such an effect had never been detected in the field. That's why we wanted to go out and collect these measurements, says Larsen, a glaciologist at the Cooperative Institute for Research in Environmental Sciences at the University of Colorado Boulder. She and her colleagues have, for the first time, measured an ice shelf flexing up and down as lakes formed on its surface and then drained away a few days or weeks later. Ian Willis drills a hole to install a metal pole on which to mount a pressure sensor in an empty lake basin at the beginning of the melt season. Larsen Banwal's team snowmobiled out from Antarctica's McMurdo Station to 4 roughly kilometer-scale meltwater lakes on the McMurdo ice shelf, drilling global positioning system stations mounted on poles into the ice at varying distances from the centers of the lakes to measure changes in the ice's height. They also placed water pressure sensors near some of the GPS stations to measure water levels in the lakes, which were dubbed Peanut Ring, Riff's Tip and Wrong Trousers. Working from November 2016 to January 2017, Banwal and her colleagues found that the ice underneath the lakes deflected downward as they filled with water during the summer melt season. As the lakes drained, the ice shelf bounced back. The largest bounces, roughly 1 meter in the case of Ring Lake, were observed near the lake centers. The GPS stations farther away showed weaker deflections, if any. The flexure is very local, which could have an impact on where related fractures in the ice occur, Banwal says. How a floating ice shelf bends, and may also fracture, in response to the filling and draining of a meltwater lake. Adapted from Fig 1. Banwal et al. 2013 GRL. Despite the significant bending they recorded, Banwal and her colleagues did not see any fractures on the McMurdo ice shelf. It is possible the lakes on this ice shelf overflow their basins before they become large enough to result in sufficient stresses, the researchers suggest. These results, published Wednesday in Nature Communications, reveal the effects of a phenomenon that has been under researchers' noses since the first explorers visited Antarctica, but was not thought to be important, and so was ignored, says Ian Willis, a glaciologist at the Scott Polar Research Institute at the University of Cambridge and a member of the research team. The findings of this paper are exciting, says Jonathan Kingslake, a glaciologist at Columbia University's Lamont Doherty Earth Observatory who was not involved in the research. It's been suggested that this kind of flexure could have caused rapid collapse of ice shelves in the past and could do so in the future. Doug McIel, Grant McDonald and Becky Goodsell stand by a meltwater stream via which one of the lakes on the McMurdo ice shelf drained. Larsen Banwal and her team have applied for funding to measure whether other ice shelves are also bouncing up and down. They plan to study ones on the Antarctic Peninsula, one of the fastest warming places on the continent and where Larsen B was once located. Higher temperatures mean more meltwater. One recent study predicted a 2-fold increase in melting in Antarctica by 2050, but it is hard to predict whether all of that water will make it into lakes that could trigger flexure, Willis says. Some of the water might refreeze, get redirected down into the ice or flow across the shelf without forming a lake, he says. These are really big unanswered questions.